The image sensor is a rich portal of information for mobile devices. While its original use was for taking pictures and video, when paired with a processor, it can now do so much more, from reading barcodes to translating text. And we envision that the next step beyond this will be in continuous mobile vision. A wearable device, perhaps a shirt clip-on or a head-mounted device, can continuously look out for ways to serve its user. For example, continuous mobile vision could help us remember faces at a party, journal our food and drink habits, navigate through a confusing building, and much, much more.
Did I remember to close the garage door?
Yes.
Advances in computer vision have created an abundance of opportunities. And because these algorithms don't require high resolutions or high frame rates, computation is often quite feasible, even on a smartphone application processor. But a bottleneck to running continuous mobile vision is that running a power-hungry image sensor would drain a smartphone battery in just a few hours. To find out why, let's look at the basic operating principles of image sensors. Image sensor pixels capture light and convert it to electrical charge, filling up capacitors. To process an image, the image sensor first enters an active readout period. Driven by a pixel clock, the capacitor's voltage is read out by an analog signal chain, which creates the digital pixel values. These values are fine-tuned with on-chip logic, which then sends the image out of the image sensor. Then the sensor enters an idle period, to wait until the next readout, which is in turn followed by another idle period. The system can request fewer pixels either by lowering the scale of the image or windowing the image. This reduces the time spent in active readout and lowers the power consumption. But the key problem is that the sensor still consumes a considerable amount of power even when mostly in idle mode. This is unacceptable for continuous mobile vision applications. We need image sensors to be energy proportional. When asking for high frame rates and high resolutions, we don't mind spending a lot of power, but for low frame rates and low resolutions, we should operate the image sensor with reduced power. This can create a manageable trade-off between power and image capture quality. We developed two simple system-level techniques that will allow mobile systems to create energy-proportional image capture on current sensors. The first is aggressive standby. As we showed, for low resolutions and low frame rates, the sensor spends a lot of power just waiting in idle mode. With aggressive standby, we request that the sensor enter low-power standby mode in between active readouts as often as possible. We still have to enter idle mode to allow the sensor to undergo exposure before capture, but the energy wasted in idle mode is significantly reduced, and so the power savings in aggressive standby mode is substantial. This allows for energy proportionality to both resolution and frame rate. Our second technique further reduces power by carefully managing the clock frequency. Inspired by clock scaling techniques for processors, we looked into the effect of clock frequency on power consumption of image sensors. As expected, a higher clock frequency allowed the sensor to read out frames much faster, but also resulted in a higher active power and idle power. Depending on the desired number of pixels, desired frame rate, and exposure, the optimal clock frequency can be analytically determined. Clock optimization allows for energy proportionality to both resolution and frame rate, and when combined with aggressive standby, we can achieve low power for low frame rate and resolution requirements. Further energy proportionality optimizations can be made at the image sensor architecture level. We direct the viewer to our paper for further details. However, even with the simple system-level techniques from this video, we're able to offer highly reduced power at low frame rate and resolution requirements. At 0.1 megapixels and 3 frames per second, we can offer as much as 95% power reduction on a typical smartphone image sensor, from 200 milliwatts to 10 milliwatts. We can incorporate these techniques in mobile systems with minimal hardware adjustment, such as including a configurable image sensor clock and changing some drivers. And at a software level, computer vision algorithms and frameworks will be able to be adapted with energy proportionality in mind. Algorithms can request low-resolution, low-power frames most of the time, while only occasionally requesting high-resolution, high-power frames. We expect that these types of hierarchical vision frameworks will mature as continuous mobile vision platforms progress. And from a user perspective, we will be able to enjoy our lives more fully as our devices supplement our limited human memory and attention. We foresee a bright future with continuous mobile vision.